So let me just do a quick presentation about SHAP. This is part of my dissertation. It's also published on the Interpretation Journal. This paper called Quantifying the Sensitivity of Seismic Phases Classification to Seismic Attribute Selection, an Explainable Machine Learning Study. So, as you know, as the machine learning models get more complicated, like we have deep learning implementations, the interpretation of these models become challenging. It's difficult to understand why this result, correct, or how the machine learning model got this result. So there is a technique in the machine developed in the machine learning community called SHAP. And the Lumber and Lee and Lumber al 2017-2018, this paper show how the SHAP technique works, but it's a recent development to enable quantitative estimation of machine learning model interpretability. So, for example, imagine that you have three phases of interest: the MTD, the salt, and the conformal sediments. And you see that there is a point, a voxel in your result that is classified as salt with 91% probability. So you want to understand how this final result. So you start with a base value. In base value, imagine that you flip a coin. So the probability of have head or tails is 50-50. So in here you have, because we balance the data set, we have a 33% of having each phase, 33% of MTD, 33% of salt, or 33% of conformal sediments. And then from this base value, it start getting the interpretation of the input attributes. For example, you have this voxel have a low total energy, so that increase the probability of having salt. It also have low coherence, so that also increase the probability. It has a high reflector convergence that increase the probability to maybe 98%, but then it has low GLC entropy, and probably you expect high GLC entropy, so that decrease the probability a little bit to the final 91%. So now we don't have just the final probability volume with 91% probability. We also have some volumes to interpret based on the attributes, like the attribute does the attribute increase or decrease the probability. So this is the workflow that we did for in our research in the paper. So the idea is like you have the seismic volume, you compute your seismic attributes. In here, we also have a sensitivity analysis. We wanted to analyze how different changes in the input affect the results. So we apply a Kuwara median filter to smooth the phases response of the seismic attributes. And then we also add random noise, band limited random noise to the data. So we have three different cases: the original seismic attributes, we have the Kuwara filter attributes, and we have the added noise attributes. Then using my data, we define some training validation data sets, we scale the data. We did some hyperparameter search to obtain a random forest and to perform the classification. And then with the random forest, we apply these SHAP values, the tree explainer, to interpret the model. So we have some global interpretability using training data. We have the SHAP dependence plot, the SHAP global feature of importance, and the SHAP summary plots. I'm going to show some of these in the next slides. And we can also have a local interpretability to explain why a certain voxel in the whole volume was classified as a particular seismic phases. So the data that we are using it's located in the Gulf offshore in the Gulf of Mexico. It was acquired by PGS. We have three target seismic phases: the MTDs, the salt, and the conformal sediments. See here, the salts are characterized by low amplitude chaotic reflectors. We have the MTDs, that is, they have a highly heterogeneous response. We see that we have some chaotic components or more coherent components inside these MTDs. And we have some conformal sediments. In the conformal sediment, we have these nice parallel high amplitude reflectors. But then as we move towards the edges of the salt piers, the seismic quality decreases, and we have some lower amplitudes in these conformal sediments. So to define the training and validation data sets for a random forest, we picked 5 vertical sections in these green polygons from A prime to F prime for training and validation. and then we have the GG prime vertical section to test the model. So this is a line outside the training validation, to evaluate the performance of the model. And when seeing this on label data set that wasn't used for training the model. So the candidate seismic attributes, we have 9 different attributes. We have the coherence, the total energy, the GLC and entropy, the reflector convergence, spectral bandwidth, GLC and contrast, the deviation, energy deviation, and convergence of deep energy. So these attributes, we select them because they were good attributes to try to differentiate between the seismic phases. As I said, we also perform this sensitivity analysis. We have the original case number 1, that is just the original seismic attributes. You have your volume, you compute your seismic attributes, in this case, coherence, for example. Then the second case is applying a Kuwara median filter. So you see that this filter is block and smooth the response, looks less noisy, smoother. With the case 3, we actually add band limited by random noise or additive by Gaussian noise. So you see that the Gaussian noise for example, in the coherence, decrease the phase separation because everything is becoming more noisy. So even the sun reflectors that tend to be high amplitude, parallel reflectors tend to be noisier, more noisy now. So we have less phase separation between the SAL, the NTDs, and the conformal elements. So then we have the random forest using, we use a machine learning framework in Python to develop the random forest classification model. And then we apply SHAP for the 3 cases. This is the global analysis. You see that we can analyze the global importance of the attributes. So what we analyze in the 3 cases is like the total energy and the deviation tend to be the most important attributes for all cases. And then depending on the quality of the inputs, if you have the Kuwara, you have your original attributes, or you actually added noise, you have noisy outputs, the importance of the attributes tend to change. So also we see that the attributes important changes also based on the seismic phases. For example, the total energy for the NTDs and the salt tend to be the most important attribute, but in the case of the conformal sediments, the deviation tend to be the most important attribute. So you see now that the attribute important, it changes, it's dynamic. It changes based on the quality of your input, but also in the phases, the target phases of analysis. These are the classification results for the original, the Kuwara, and the signal to noise ratio equal to 2, or adding seismic noise. We see that the best results are retaining with the Kuwara when Kuwara median filter is used. We see that we have better response for the conformal sediments. You see that the noisy part, it tends to misclassify a lot of the conformal sediments close to the salt appears. But in the Kuwara, that decreases. Still, we have some misclassification. You see that part of the conformal sediments, the deepening conformal conformal sediments are close to the salt appears are misclassified as NTDs by the algorithm. So of course we have some misclassification, and we need to do the QC and the interpretation. And also we have multiples. You see these multiples because we didn't train the random forest for multiples. They tend to be misclassified either as conformal sediments or NTDs. So as I said, we need to do QC, we need to interpret the results. So in general, we have really good results, but we have some misclassification in the seismic phases as expected. So after that, we can have our output. Usually what you can have in machine learning is a probability volume. You can analyze the probabilities. Well, now with SHAP, you can select a voxel, for example, this voxel A, that we see this inside the salt appear, but it was misclassified as a NTD. So it was misclassified as an NTD with 45% probability. So now with SHAP, we can analyze how the attributes were used. So we have the plot. We see that the coherence from the base value of 33%, the coherence, the spectral bandwidth, the deviation, and the total energies tend to increase the probability, while the GLC entropy and the covariance deeper energy tend to decrease the probability. So when you have your base value and you take into consideration the attributes, you see that some of them increase the probability, some of them decrease the probability to the final output of 45%. So now with SHAP, we are able to actually analyze in detail or add more interpretability to the model. Also, if you use your vertical sections, apply SHAP and correct that with the original volume, you can analyze how the random forest or the machine learning model sees the geology, you know. So in this case, you see that the total energy, for example, for the NTDs, the total energy is classifying is increasing the red is meaning that it's increasing the probability. So the total energy increases the probability for the NTDs, for the salt really well. But you see that we have some overlap for the conformal sediments. You see that the total energy tend to increase the probability for the conformal sediments, but also for some NTDs. For the deviation, you see that the deviation is classifying really well the NTDs, the conformal sediments, but then in the salt, it's classifying really well the salt, but some of the part of the NTD are also misclassified. So you see now that we can actually analyze how the random forest sees, you know, the data, but also we definitely see that there is some overlap between the seismic phases. So some conclusions for this analysis is the attribute important is dynamic and changes based on the quality of the input data and the seismic phases analyzed. The combination attribute that measure changes in energy and depth are the best features to discriminate between NTD salts and conformal sediments. And this in context interpretation that we have here allow to analyze how changes in the seismic reflector are impacting the classification. Based on the particular seismic attributes, an overlap between the NTD salt and conformal sediment might occur in the study area. So what we see is that some attributes are better than others to differentiate between the seismic phases. And for a reason, you use this multi-attribute classification to take advantage of these attributes that, okay, these two attributes are better to differentiate between NTDs and salt. These two other attributes are better to differentiate between salt and conformal sediments. These other two between conformal setting and NTD. So you want to take into consideration all these attributes to have a better classification. So that is just a short presentation of that work. And as I said, it's a published on the Interpretation Journal. So as Heather said, we have more time to integrate that on AASPI. So the goal is to give you the option to actually apply SHAP random forest to your data. Let me just open AASPI real quick. Okay, so it's on the machine learning toolbox. Let me show you really quick. We have some data here. So this is the Cora data set. We have some a volcano there. I already picked some polygons. Let me show you really quick. For example, here, training one volcano. So I just picked some polygons with my facies of interest, for example, or training one volcano. So I already picked the polygons I keep it as a step here, but you go to supervised learning. As I said, we have the plot and the 5 polygons. I already did that. Then I need to convert the polygons to point sets. So, okay, you select the polygons. These are my polygons of interest. You define your seismic volume of reference. I don't know, this is Jan2023. I'm going to do some decimations because I don't need every point inside the polygons. I'm going to do that. So that's the second step. Then you go to supervised learning. Then I'm going to extract the attributes. I'm going to use some attributes. Here's the coherence, contrast, entropy, and total energy. Then I look for my point sets. You see that it automatically identifies the phases. Okay, that looks good. Then just extract that to create my training data using these 4 attributes. And then I'm going to the machine learning toolbox, supervise, going to analyze input training data. So I'm going to select my training data. These are the attributes. See that we have energy ratio, contrast, GLC contrast, GLC entropy, and the total energy. I'm going to keep the default with Z-score normalization right now. And then we have a new random forest here. For the random forest in the analyze input, you can actually do the hyperparameter search. You select the hyperparameters for a random forest. I'm going to just to change the number of trees, but I'm going to keep the rest as default. You can select the number of iterations. Right now, you just test 20. Your cross-validation is split. Also, hyperparameter random seed for the hyperparameter search, so you can repeat your analysis. And then I'm going to apply SHAP because I want to do my machine learning interpretation. So right now, just running. Okay, testing is doing the hyperparameter search. See here. So give it some time. Okay. So these are the results. It will automatically look for the best model, and using that best model, it will apply SHAP. Okay. So these are the SHAP plots. First, it gives me general attribute importance. Just change it here a little bit. Okay. So based on my analysis, I see that for this particular data, these attributes and these polygons that I picked for this demo, see that the total energy is the most important attribute, then followed by the GLC and contrast, the coherence, and the GLC entropy. You see that the mean SHAP value, it means like the average importance of the attribute for the model, and the total energy is the most important one for both phases. Then I can have my summary plots. I didn't show that in the presentation. It was a shorter presentation. But for example, here, you can have a force plot, a summary plot, sorry, for each phases. So for example, for the volcano phases, see now that the total energy still is the most important attribute. But now with this summary plot, you can interpret the values. Like, for example, positive SHAP values, it means that it's increasing the probability. Negative SHAP value, it means that they are decreasing the probability. So I see here that the total energy, low values of total energy are increasing my probability of having a volcano phases. That I expect that because tend to be characterized by low amplitude chaotic reflectors, so lower total energy. Higher GLC and contrast also are increasing the probability of having that phases. Here it's not that clear with the energy ratio. In general, lower values, but there are some values that are increasing, high values that are increasing the probability. So I will need to analyze more of that in detail. And then higher values of GLC entropy, as I said, they tend to be the least important attributes, but in higher values of GLC entropy are increasing the probability for the volcano phases as well. So that's what I expect. Lower values of energy, higher values of GLC entropy, higher values of contrast, sorry, higher values of GLC entropy. Usually it should be lower values of coherence. I see that, but there are some values, high values of coherence that also increase the probability. They might be misclassification with other phases, but more detail can be done to analyze that. If you analyze the summary plot for the non-volcano, it's just the opposite response because it's a binary classification. Tend to be a little more complicated when you have more than two phases. But here, as expected, lower values of total energy tend to decrease the probability of having these phases. As you see, they have negative SHAP values. There are some values as well that are increasing the probability, maybe some misclassifications. GLC and contrast, lower values of GLC and contrast tend to increase the probability of non-volcano phases. So if you want to analyze higher GLC and contrast values tend to decrease the probability. Same with the entropy, lower entropy. And in here, it's very clear that actually high values of coherence tend to increase the probability of non-volcano phases because what I pick tend to be this high amplitude parallels, non-conformal sediments outside the volcano, So that's expected, and it's very clear. Higher values of energy ratio tend to increase that probability. So you see now with SHAP, you can create your model and you can do a very detailed interpretation for your model. You can interpret now how the model is using the input attributes to classify the faces. So yeah, that's what I have right now for the SHAP analysis. Any